Good morning all. In this lecture, I will explain landau diamagnetism. In the previous lecture, we discussed about polyparamagnetism, and in this lecture, we will discuss about diamagnetism. What is the origin of diamagnetic character in a material and all. Okay. So, what is diamagnetism? It basically arises from the quantization of the orbital motion of charged particles in presence of an external magnetic field. Okay, so materials will show diamagnetic property only in presence of an external magnetic field, and those materials should contain charged particles. Okay, now suppose you are applying a uniform magnetic field along the z direction. You can see the three axes here, x, y and z, and your external magnetic field is along the z direction. Suppose there is a charged particle having velocity v, then the Lorentz force experienced by the particle is given by E v cross b divided by c, where c in the denominator is because we are expressing in CGS units. In SI units, this c will not be there. And here E is charge of the particle, v is velocity and b is magnetic field. We can split this velocity vector into two components, one along the field direction and one in a direction perpendicular to the field, that is in the xy plane. So we will have two components of velocity, one is Vz. That Vz will produce a motion along the z direction and Vxy will produce a circular motion. Why? I will explain. This Vz cross b will be 0 because Vz and b are parallel. Therefore, Lorentz force will be 0. Lorentz force 0 means there will not be any force, that is, it is a uniform motion along the z direction. So kinetic energy will be constant, it is pz square by 2. So along the field direction, the particle will move with uniform velocity because there is no force in that direction. But Vxy cross b, that will be Vxy b sine 90, and it is Vxy b because sine 90 is 1. So the Lorentz force is given by E into Vxyb divided by c. And the direction of this force will be perpendicular to the velocity and magnetic field. Magnitude is E v b divided by c, and direction is always perpendicular to velocity. The only motion in which force is always perpendicular to velocity is circular motion, where velocity is tangential and force is along the radial direction. So the particle will move in a circular path perpendicular to the direction of magnetic field. And for circular motion, we know that there will be a centripetal force, and that centripetal force is actually provided by this Lorentz force. So we can equate this centripetal force mv square by r with the Lorentz force. One v will cancel, so you will get mv divided by r equal to eb by c. V you can substitute in terms of angular velocity, and it is r omega. So mr omega by r equal to eb by c. So omega is eb by mc. So in a plane perpendicular to the magnetic field, the particle will move in a circular path with angular velocity eb by mc. Okay, so the particle will have two motion. One is parallel to the direction of field, which is with a uniform velocity, and one is perpendicular to the direction of field, which is a circular motion with angular velocity eb by mc. The total kinetic energy of the particle will be px square by 2m plus py square by 2m plus pz square by 2m. Now, if we treat quantum mechanically, the energy associated with the circular motion is quantized, and we can say that in circular motion the classical energy expression is px square by 2m plus py square by 2m, This will get replaced with the quantum mechanical energy J plus half into h cut EB by mc. Okay, for understanding this, you can compare with the two-dimensional harmonic oscillator case. Classical oscillator, the kinetic energy is px square by 2m plus py square by 2m. But quantum mechanically, the energy of two-dimensional harmonic oscillator is n plus half h cut omega, where n is a quantum number and omega is frequency of the oscillator. And in an exactly similar manner, here instead of the frequency of oscillation, we have frequency of rotation EB by mc. So replace this omega with EB by mc, and quantum number we used a letter J. Here again J can take value 0, 1, 2, 3, etc. So the motion perpendicular to the direction of magnetic field, that circular motion, the energy is quantized. Okay. Now the energy associated with the linear motion along Z is also quantized, but due to the smallness of energy intervals, the energy levels are lying very close to each other, so we can treat it as a continuous variable. Therefore, the total energy of a charged particle which is moving in presence of a magnetic field can be written as E h cut b by mc J plus half plus pz square by 2, where J can take values 0, 1, 2, etc. Okay. Now, the quantized energy levels are degenerate because they result from a coalescing together of an almost continuous set of zero field energy levels. These quantized energy levels actually formed from a coalescing of a large number of zero field energy levels. So there will be some degeneracy. I will explain this concept. Look at this figure. This is a set of, the left side you have a set of almost continuous energy levels, that is with the magnetic field 0. When you apply a magnetic field, these levels becomes quantized. These continuous energy levels becomes quantized energy levels. So without field you have a continuous energy level, with the field you have discrete energy levels. So these discrete energy levels actually formed by coalescing this set of levels. Okay. Now this portion, the levels whose kinetic energy lies between EB h cut by mc J and EB h cut by mc J plus 1 coalesce to form a single level characterized by quantum number J. What is the meaning? Suppose you consider J as 0, then this value will be 0, this value will be EB h cut by mc. So the levels between 0 and EB h cut by mc joined together to form a single level with the quantum number J equal to 0. If you put J equal to 1 here, it means that the level from E h cut b by mc to 2 E h cut b by mc coalesce together to form a single level with the J equal to 1, and so on. So these set of levels coalesce together to form a single level. These set of levels coalesce together to form a single level, and so on. Okay. Now, how many levels are there to coalesce together to form a single level? Okay, what is the number of levels included in this single discrete level? How many continuous levels are there? That is the question. So the number of levels that coalesce, that is given by 1 by h square integral dx dy dpx dpy. From where we obtained this expression? We have the idea of phase space. For a system of 1 degree of freedom, phase space will be two-dimensional, and it is a space spanned by coordinate and momentum. So if you consider this phase space, you have along horizontal axis the coordinate x, along the vertical axis momentum px. And you can consider a finite area in this phase space whose value is Planck's constant, and this will give you a particular state. Okay, from the idea of classical phase space, each microstate can be represented by a finite area in the phase space. So that area is essentially the Planck's constant h. So how many states are there in this phase space? So you calculate the area of allowed region of phase space, then divide with this fundamental area. You will get the number of states. In a system with 2 degrees of freedom, the phase space will be 4-dimensional. It is not possible to draw that phase space. But the volume of phase space, then I will call that volume. That will be dx, dy, dpx, dpy. Integrating that over the allowed region, then you will get the total volume. Divide with the fundamental volume. In 2 degrees of freedom, fundamental volume will be h square. For 1 degree, it is h raised to 1. For n degree, it will be h raised to n. So it is 1 by h square integral dx, dy, dpx, dpy. This will give you the total number of levels. And the integration of dx, dy will give you Lx into Ly. If you are considering a rectangular box with a length Lx and breadth Ly, then this integral dx, dy will give you Lx, Ly by h square. The remaining is integral dpx, dpy. That is nothing but area of momentum space having width Po minus Pi. What is the meaning of that? You consider the momentum space. Along the horizontal axis it is Px, along the vertical axis it is Py. Then dpx is a small length along Px, dpy is a small length along Py. Dpx, dpy is a small area element. You have to integrate this over this shell. But since this shell is of circular symmetry, instead of Cartesian coordinates, you can use polar coordinate. So dpx, dpy becomes p dp d theta. This is polar because you know that in xy space, instead of dx, dy, you have r dr d theta. Similarly, instead of dpx, dpy, you will have p dp d theta, and the limit of p is from pi to po. Pi is the inner radius, po is the outer radius. Theta will vary from 0 to 2 pi. If you integrate that, you will get pi into po square minus pi square. What is po square? P square is 2me. So p square is 2m into energy is E h cut b by mc into j plus half. For po square, you put j is j plus 1. For pi square, you put j as j. Okay, because you are calculating the difference of jth and j plus 1th level. So that will give you po square is equal to 2 eh cut b by c, j plus 3 by 2. Pi square is 2 eh cut b by c, j plus half. The difference. Taking the difference, you will get Lx, Ly by h square into pi into that difference is 2 eh cut b by c. So the total number of levels is Lx, Ly into Eb by hc. The interesting fact is that this number is independent of j. That is, the number of levels in this interval, all will be the same. Irrespective of the value of j, the number of levels that coalesce together to form a discrete level will be the same. And that number is given by Lx, Ly into Eb by hc. Okay, now we are going to calculate the grand partition function of the system. And it is a log theta equal to sigma log 1 plus z e raised to minus beta e, where E is the energy of the system, and the summation, this energy depends on j as well as pz. So you have to sum over various values of j as well as various values of pz. Now you can replace the sum over pz with integral because pz is almost a continuous variable. So you can replace the sum over pz with the integral along with the degeneracy. That will give you integral Lz dpz by h. And the summation over j, you have to keep it as such because j is still a discrete variable. So you have to write the sum over j equal to 0 to infinity, and the degeneracy factor of this discrete levels Lx, Ly, Eb by hc log 1 plus z into e raised to minus beta. Instead of energy, you can substitute the value we write earlier, E h cut b by mc, j plus half plus pz square by 2m. This is log theta. For high temperature, fugacity z will be less than 1. then log 1 plus za is approximately za, because log 1 plus x is x minus x square by 2 plus x cube by 3 minus etc. For very small x, you can neglect the higher order terms and you can write it as approximately x. Therefore, log theta equal to integral minus infinity to infinity Lz dpz by h sigma j equal to 0 to infinity Lx Ly Eb by hc into z e raised to minus beta eh cut b by mc j plus half into e raised to minus beta pz square by 2m. So log theta equal to z Veb by h square c. This Lz, Lx, Ly, the product of all the three will give you the volume of the rectangular box, that is V. Then there is a z, there is Eb divided by h square c. Integral minus infinity to infinity e raised to minus beta pz square by 2m dpz. Then this summation over j e raised to minus beta eh cut b by mc j plus half. So log theta equal to z Veb by h square c into this integral will give you a value square root 2m pi by beta. This summation will give you a value 2 sin h beta eh cut b divided by 2mc whole raised to minus 1. I will explain how we obtained these two terms. Okay. First, consider this integral. Integral minus infinity to infinity e raised to minus beta pz square by 2m into dpz. Put square root beta by 2m into pz equal to t. dpz becomes root 2m by beta dt. Substituting that values, you will get e raised to minus t square root 2m by beta into dt. Square root 2m by beta you can take outside. The remaining is actually gamma function. It is gamma half. Gamma half is root 2 pi. Substituting that value, you will get square root of 2 pi m by beta. Okay, so this integral is square root 2 pi m by beta. Next, this summation. When you put j equal to 0 for this summation, you will get e raised to minus beta eh cut b by 2mc. When you put j equal to 1, you will get e raised to minus beta eh cut b by mc into 3 by 2. When you put j equal to 2, you will get e raised to minus beta eh cut b by mc into 5 by 2 and so on. This is a summation, sum to infinity of a gp with first term e raised to minus beta eh cut b by 2mc and common ratio e raised to minus beta eh cut b by mc. And you know that the sum to infinity of a gp Sn is a by 1 minus r. First term is a, common ratio is r. Substituting that value, you will get like this. And take this quantity to the denominator. Then 1 divided by this quantity becomes e raised to plus beta eh cut b by 2mc. This quantity divided by this numerator will give you e raised to minus beta eh cut b by 2mc. Okay, 2mc. Now the denominator is actually 2 sin h beta eh cut b by 2mc. So the final result is 2 sin h beta eh cut b by 2mc whole raised to minus 1. Okay, so finally we obtained an expression for log theta. It is z Veb divided by h square c 2 pi m by beta raised to half 2 sin h beta eh cut b by 2mc whole raised to minus 1. Okay, from the results of grand canonical ensemble in lecture number 15, we obtained an expression for equilibrium number of particles. N bar is equal to z dou by dou z of log theta at constant volume and temperature. Here, since B is uniform, magnetic field is uniform, we can say that it is at a constant B also. So take the derivative with respect to z. Take the derivative with respect to z of this quantity. You will get then multiply with a z. Z Veb by h square c 2 pi m by beta whole raised to half 1 by 2 sin hx. Where I replaced this entire quantity with x. Beta eh cut b by 2mc. Call it as x. Okay. Then multiply numerator and denominator with an h. Already z Veb by c is there. 1 by h square is there. Multiply numerator and denominator with an h. Then 2 pi m. 1 by beta is kt. So 2 pi m kt. Instead of half, I write it as 3 by 2. So I have to divide it with the 2 pi m kt into 1 by 2 sin hx. Now this h square into h becomes h cube. H cube divided by 2 pi m kt raised to 3 by 2. It is nothing but lambda cube, where lambda is thermal de Broglie wavelength. And this EB and this h by 2 pi, EB h cut by 2mc. That is nothing but EB h cut 2 EB h cut divided by 2mc. Along with the beta, it is x. Okay, it is x. So here this kt is actually beta. 1 by kt is actually beta. So this is beta E h cut b by 2mc. The remaining times you can call it as x. So n bar is zv divided by lambda cube into x by sin hx. Okay, we got a nice expression for the total equilibrium number of particles. Now magnetic moment m, it is actually the mean value of minus dou h by dou beta. Okay, this h is actually Hamiltonian of the system, the total energy of the system. This is not beta, this is b. Okay, magnetic field minus dou h by dou b. And we can show that it is equal to 1 by beta dou by dou b of log theta to constant ZVT. This expression we already derived in lecture number 14. Okay, in the case of statistics of paramagnetism. Now m is 1 by beta dou by dou b of ZVEB. This log theta, the value we obtained, you substitute here. There are two terms containing b. One is this one and one is in the argument of sin h. Okay, so you have to apply product rule. First you keep ZVE by h square c 2 pi m by beta raised to half 2 sin h beta e h cut b by 2mc whole raised to minus 1 as constant. Take the derivative of b. Derivative of b with respect to b is 1. So you got the first term plus then you keep this terms as constant. Then take the derivative of 1 by sin h of this quantity. 1 by sin h derivative is minus 1 by sin h square beta e h cut b by 2mc. Sin h derivative is cos h beta e h cut b by 2mc. Again you take the derivative of this quantity, that is beta e h cut by 2mc. From first term and second term you can take this quantity outside. ZVE by h square c 1 by beta pi m by 2 beta whole raised to half. Then in the first quantity you will have 1 by sin hx, 1 by sin hx, and in the second time you will get minus x cos hx by sin h square x. Okay, where x is beta e h cut b by 2mc. So you can write a magnetic moment like this, but you can replace this term, this entire term outside the bracket by mu effective by lambda cube. What is mu effective and lambda cube? Lambda cube is the cube of thermal de Broglie wavelength, we already defined. Mu effective is actually Eh by 4 pi mc and it is nothing but a Bohr magneton. Okay, mu effective. And if you divide these two quantities, you can calculate that quantity and that will be exactly the quantity which lies outside this bracket. So you can write m as ZV by lambda cube mu effective into 1 by sin hx minus x cos hx by sin h square x. This is not sin square hx, it is sin h square x. Okay. Now you can divide m with n. We already obtained an expression for n and we now obtained an expression for m. So m by n bar is equal to mu effective into 1 by sin hx minus x cos hx by sin h square x into sin hx by x. That will give you m is equal to n bar into mu effective into 1 by x minus cot hx. You can take a negative sign outside, minus n bar mu effective into cot hx minus 1 by x. This cot hx minus 1 by x, it is nothing but Langevin function. We already introduced this function in lecture number 14. So magnetic moment, net to magnetic moment is minus n bar mu effective into L of x. Exactly similar results we obtained in the case of Langevin paramagnetism, lecture number 14. But here there is an additional negative sign that indicates the diamagnetic nature. Another interesting another interesting fact is that here it depends on mu effective. What is mu effective? Eh by 4 pi mc. So the presence of Planck's constant through mu effective in the value of magnetic moment implies that when h tends to 0, m will tend to 0. So diamagnetism is a consequence of quantum behavior, because Planck's constant is introduced from the quantum nature of the particle. So the quantum behavior is the reason for diamagnetism. If this h tends to 0, this magnetic moment will go to 0. So it is known as Bohr-van Leeuwen theorem, and it states that diamagnetic phenomenon does not arise in classical physics. Diamagnetic phenomenon arise only in quantum physics. Okay, so that is another characteristic. Now we will calculate the quantity for low magnetic field and high temperature, that is mu effective B by kT less than 1 for this special case. Then this sin h of this quantity becomes that quantity itself, because for very small x, sin hx will be approximately x. Okay, sin hx will be approximately x. Then n bar becomes n bar is actually zv by lambda cube x by sin hx. X by sin hx becomes 1. So this will give you z is equal to small n bar lambda cube. Small n bar lambda cube, where small n bar is capital N bar by v. Okay, so for high temperature, fugacity is n bar lambda cube. We already have this relation earlier. For high temperature, we know that fugacity is very much less than 1, and from lecture number 29, we can write fugacity z approximately equal to f of f3 by 2 of z. This is actually Fermi-Dirac function. For very small z, f3 by 2 of z is approximately z, and f3 by 2 of z is nothing but n lambda cube. So from here also you have z is equal to n lambda cube relation. So from the concepts of diamagnets also we could reproduce that relation. Now magnetization, net magnetic moment m is equal to minus n mu effective into x by 3. In this range, for low B and high temperature, x is very small, cot h minus 1 by x becomes approximately x by 3. For very small x, cot h minus 1 by x becomes x by 3, and you substitute for x, we will get final answer as minus n into mu effective square B divided by 3 kt. So m is equal to minus n bar mu effective square by 3 kt into B. Chi infinity, the low field susceptibility is m divided by Vb, and that is equal to minus n bar mu effective square divided by 3 kt. So this is the diamagnetic counterpart of Curie's law. We obtained the same Curie's law in paramagnetism also, but that was actually plus n mu b square divided by kt or so. Okay, plus that was positive in sign, and there is no 1 by 3. There is no 1 by 3 in paramagnetic case. Okay, so chi infinity is actually n mu square divided by kt for paramagnetism, but for diamagnetism it is minus n mu effective square divided by 3 kt. Another important aspect is this chi depends on mu effective square, that is it depends on EH by 4 pi mc whole square. So irrespective of the sign of the charges, if it is an electron it will be minus E, if it is a proton it is plus E, but it is the square, chi depends on the square. So irrespective of the sign of the charged particles, this diamagnetic phenomenon exists. Okay, so diamagnetic property is independent of sign of charged particle, whether it is positive or negative. If there is an orbital motion in presence of a magnetic field, there will be diamagnetic property. Okay. Now net magnetization of an electron gas. Now you have expression for paramagnetic susceptibility as well as diamagnetic susceptibility. So the net magnetization, you can write it as the sum of these two. What is for t tends to infinity, chi infinity of paramagnetism, it is n mu b square divided by kt. And for diamagnetic case, chi infinity of dia is minus 1 by 3 n mu prime b square divided by kt. This mu effective, I will write it as mu b prime. Actually mu b is EH by 4 pi mc. Here mu b prime is EH by 4 pi m prime c. This m prime is actually effective mass. Okay, here the diamagnetism arises due to the motion of electrons in a magnetic field. In an applied field, when electron moves, the mass will get modified, and that mass is known as effective mass. So you have to use that mass for the calculation of this quantity in diamagnetism. This paramagnetism actually arises from the intrinsic magnetic moment, so there is no need to change that. So the net magnetic moment is given by n into mu b square minus 1 by 3 mu b prime divided by kt. 1 by 3 mu b prime square divided by kt. This is the net magnetic moment of electron gas. Okay. Now the diamagnetism, this expression we derived only at high temperature range, right? A high temperature. For high temperature, we derived all these calculations of diamagnetism. Okay, but now we need an expression which is applicable for all temperatures. So diamagnetism at all temperatures. For finding a result which is valid for all temperatures, still we need an assumption. We are assuming that the magnetic field is very low such that at all temperatures mu effective B is very much less than kT. If this condition is valid, we can use Euler summation formula, and it is given by sigma j equal to 0 to infinity f of j plus half is approximately equal to integral 0 to infinity f of x dx plus 1 by 24 f prime 0. Okay, this is Euler summation formula. Now we have to apply this formula in our case. Our expression is log theta equal to VEB by h square c integral minus infinity to infinity dpz into sigma j equal to 0 to infinity log 1 plus z e raised to minus beta eh cut b by mc j plus half into e raised to minus beta pz square by 2. We have to replace this sum with the integration. So this sum will get replaced with integral 0 to infinity dx. At the same time, you have to replace all the j plus half with the x. J plus half with x. That will give you this first term. Plus, there is one more term. 1 by 24. What is the second term? F prime 0. So, you have to calculate the derivative of this quantity. With respect to j plus half. Then put j plus half equal to 0. What is derivative of this quantity? 1 divided by logarithm of this quantity. Derivative is 1 divided by 1 plus e raised to minus beta eh cut b by mc j plus half into e raised to minus beta pz square by 2. But the derivative is with respect to j plus half. So you have to take the derivative of this quantity z e raised to minus beta eh cut b by mc into j plus half into e raised to minus beta pz square by 2. Again, you have to take the derivative of this quantity. That will give you minus beta eh cut b by mc. Minus beta eh cut b by mc. Okay, so log theta equal to this first term is here. Okay, this first term is here. In the second term, when you put j plus half equal to 0, this term will be 1. E raised to 0 is 1. The remaining term in the numerator is z e raised to minus beta pz square by 2. Here, when you put j plus half equal to 0, the denominator will be 1 plus z e raised to minus beta pz square by 2. So you can take this z e raised to minus beta pz square by 2 to the denominator. Then 1 by this quantity becomes z raised to minus 1 e raised to beta pz square by 2 plus z e raised to minus beta pz square by 2 divided by z e raised to minus beta pz square by 2. That will give you 1. Okay. And then the remaining terms here, eh cut becomes eh by 2 pi mc. If you multiply with a 2 and divide with a 2, this eh by 4 pi mc becomes mu effective. There is a b, there is a beta, and 2 by 24 becomes 12 and this negative sign. So that second time becomes minus beta b mu effective by 12 integral minus infinity to infinity dpz by z raised to minus 1 e raised to beta pz square by 2m plus 1. Okay. Now we will concentrate on this second term. The VEB by h square by c is h square c is common. So multiply VEB by h square c with the second term and consider that term. Okay, this one minus VEB by h square c beta mu effective b divided by 12 integral minus infinity to infinity dpz by z raised to minus 1 e raised to plus beta pz square by 2m plus 1. Put y equal to beta pz square by 2m. Pz becomes root 2m by beta into root 2y. dpz becomes root 2m by beta into 1 by 2 root y dy. Substitute all these values here. You will get minus VEB by s square c is outside, 1 by 12 beta mu effective b square root m by 2 beta, square root m by 2 beta. This is actually this thing, integral minus infinity to infinity. This 2 and this root 2 becomes a root 2 in the denominator. That is why it is square root m by 2 beta. Integral minus infinity to infinity y raised to minus half dy divided by z raised to minus 1 e raised to y plus 1. Okay. But mu effective is EH by 4 pi mc. So EH equal to mu effective into 4 pi mc. EH equal to mu effective into 4 pi mc. So you multiply here with an h and divide with an h. Then this h square becomes h cube, and the numerator EH you can replace it with mu effective into 4 pi mc. Remaining is mu effective by 12. This beta and this root beta in the denominator becomes root beta in the numerator. So that will make it square root of m beta by 2. Okay, this b and this b becomes b square. I think all terms are correct. Then integral minus infinity to infinity you can replace it with 2 times integral 0 to infinity. 2 times integral 0 to infinity y raised to minus half dy divided by z raised to minus 1 e raised to y plus 1. Okay, this 2 and this 12 becomes cancelled and it is 6 minus pi v. Okay, so this mu effective and this mu effective becomes mu effective square and this b square. So make it mu effective into b whole square. This beta raised to half, beta raised to half. Remaining terms, this there is 2 here, there is root 2, this 2 cancelled, right? This 4 and this root 2 becomes 2 root 2 in the numerator, that is 2 raised to 3 by 2. This m and this root m becomes m raised to 3 by 2, that is 2m raised to 3 by 2. So it is minus pi v by 6h cube, 2m raised to 3 by 2, mu effective into b whole square, beta raised to half, integral 0 to infinity y raised to minus half dy divided by z raised to minus 1 e raised to y plus 1. Okay. Now the first time here, this first time is actually independent of b. There is no dependence of b. Actually there is a b here and here, but if you replace the variable x with the bx, if you replace the variable x with the bx, that integral remains invariant. So we can say that that integral is invariant under the transition x to bx. Okay, so if an integral is invariant under the transition x to bx, that means that integral is independent of b. Why that is independent? Because you look at the structure of that term. In the argument of exponential there is a bx. I highlighted here using a red bracket. Also in the integral there is a b dx. So here it is bx, here it is b dx. If you replace bx with x prime, this b dx becomes dx prime. So these two integrals are exactly the same. Okay, so we can say that this first term is independent of b, even though we can see that there is b, but eventually that term is actually independent of b. That integral is actually independent of b. So what is the significance of that statement? It is independent of b. When we calculate the net magnetic moment, that is a derivative with respect to b. So if a term is independent of magnetic field, no need to take the derivative. Okay, or that derivative will give you 0 value. So for calculating m, 1 by beta into dou by dou b of, you take the derivative of only second time. Okay, actually log theta contains 2 terms, but the first time is actually independent of b. So if you take the derivative, that will vanish. So we are going to take only the derivative of second time. But there is only a b square dependence, that becomes 2b. All other terms are constant. Okay. So you will get this relation. But this last integral, you can write it in terms of Fermi Dirac functions. The definition of Fermi Dirac function f half of z is 1 by gamma half integral 0 to infinity y raised to minus half dy divided by z raised to minus 1 e raised to y plus 1. So inverting this, you will get integral 0 to infinity y raised to minus half dy divided by z raised to minus 1 e raised to y plus 1 equal to root 2 pi into f half of z, because gamma half is root pi. Substituting for this integral, you will get this quantity, and rearranging this, you will get the value of chi low field susceptibility is nothing but net magnetic moment divided by Vb. This V and this B will cancel. The result is minus mu effective square 2 pi m raised to 3 by 2 divided by 3 h cube beta raised to half into f half of z. Okay, where mu effective is EH by 4 pi mc. Again, this diamagnetic character is irrespective of the sign of charged particle, because it contains mu square. Mu contains charge, so if you change the sign, it will change, but mu square will remain invariant. So diamagnetic character is irrespective of the sign of charged particle. This is the general relation for susceptibility. We can check whether we will get the old relations in the limit t tends to infinity and t tends to 0. Okay, first we will consider high temperature case. Z less than 1. So f half of z is approximately z, and it is nothing but n bar lambda cube. Substitute that value. Solving, you will get minus 1 by 3 n bar beta mu effective square. It is minus 1 by 3 n bar mu effective square divided by kt. Exactly the same result as we got earlier. In the low temperature limit, T less than Tf. So z is very much greater than 1. F half of z you can write approximately equal to 2 by root pi log z raised to half. Now we can substitute this value of f half of z in the equation for chi. Then we will get minus mu effective square 2 pi m raised to 3 by 2 divided by 3 h cube beta raised to half into 2 by root pi log z raised to half. But the chemical potential mu is kT log z. Also chemical potential mu is Fermi energy at low temperature. So log z raised to half becomes EF by kT raised to half. So it is EF beta whole raised to half. Substituting this value for log z raised to half, you will get minus mu effective square by 3h cube 2m raised to 3 by 2 2 pi into EF raised to half. This is valid only at as t tends to 0. Now the Fermi energy EF is given by 3n by 4 pi v raised to 2 by 3 h square by 2m. So 2m raised to 3 by 2 by h cube is actually 3n by 4 pi v 1 by EF raised to 3 by 2. Substituting for this 2m raised to 3 by 2 by h cube, this 3 will cancel, 2 pi will cancel with this 4 pi, and remaining there will be a 2. N by v becomes n bar, small n bar. So the answer is minus mu effective square 1 by 2 small n bar divided by EF, because here you have an EF raised to 3 by 2, here you have an EF raised to half. So the remaining is EF in the denominator. So the diamagnetic susceptibility at 0 Kelvin is minus half n bar mu effective square divided by EF. If you compare it to the paramagnetic result, it was plus 3 by 2 n bar mu star square by EF. So there is a sign change. This sign, negative sign, indicates that it is diamagnetic in character, and the magnitude is only 1 by 3rd of paramagnetic susceptibility. Magnitude is only 1 by 3rd of paramagnetic susceptibility, and another difference is this mu star is intrinsic magnetic moment of molecules, and here this mu effective, here mu effective is actually EH by 4 pi mc, EH by 4 pi mc. So you have to replace this mu star with the mu effective, then this chi 0 is minus 1 by 3 of chi 0 paramagnetism. So paramagnetism basically arises from the intrinsic magnetic moment of the particles, but diamagnetism arises from the motion of charged particles in a magnetic field. Okay, and the velocity, you can split it into two components, one along the direction of field, one perpendicular to the direction of field. The perpendicular component will take the particle in a circular path, and that orbital motion is quantized, and that quantization results in the diamagnetic property of material. Okay, thank you.